Hello, welcome back to Capacitor Programming Language. Today we're going to talk about functions and higher order functions. Let's define a function max. When a is bigger, return a, otherwise return b. Let's try it out. So this will take the maximum of two numbers. Seems to be working. Now let's define a minimum. We can do this in one line. All we have to do is call max with negative arguments and then take the negative of the result. So let's try to call min. So 1/4 should be less than 1/3. All right. We can also specify the return type of a function. And we can specify the types of the parameters too. So now if you try to call min and max with the wrong types, it will give you an error. We can still use them on any numbers. This one is 10 to the power of 80, 2 times 10 to the power of 75. But if we try to give it some string arguments, we get this error. Alice is not of type number and Bob is not of type number. Let's go back. Let's define a fold. This will fold up a list using a function. So notice we're passing in a function f to the function fold. So when the list has a length of 2, we just want to apply a 2-argument function to both elements of that list. Otherwise, we want to fold up the rest of the list. So we call f, and we need to make a recursive call to fold. So list.slice1, that will chop off the first element of the list and give you back the rest of the other elements. So let's define some simple functions, plus and times. Import the file again. Now we can fold plus on 1, 2, 3, 4, and it will give us the sum of 1, 2, 3, and 4. If we use times, it will give us the product of all the numbers in the list. We can even use min and max. So if we want the minimum number in the list, we can just do this. -5 is the smallest number in that list. We can change this to max. 38 is the biggest number in the list. So that just works. Great. So not only can we pass functions into other functions, we can return them too. So let's create a function inside of a function called get. And what get does is that it will take an integer index and return a particular value depending on the index. And we can reference x, y, and z, those variables that were passed to container itself. If we return get, we have a function that returns another function. So let's create a new container. We'll give it 3 arguments. If we pass it an index of 1, we get the second element. Index of 0 will give us the first element. Index of 2 will give us the third element. Any other index will give us the last element. But notice that my list is not really a list, it's a function that remembers information from where it was defined, specifically the variables x, y, and z. Let's try a simpler example. Make adder. We want to generate a new function called add that only takes a single argument, but add can remember the contents of value, even though value wasn't passed as an argument to add. It was passed as an argument to make adder. So we can create an add 5 function that adds 5 to whatever it receives. We can make a different function called add 10. Let's try it out. So we can make a add 2 function right here and call it like this. All right. So this is the definition of a derivative as a limit. So if you've taken Calculus 1, you've definitely seen this before. Now what we can do with this is write a function called differentiate, which takes a function f, and we wanted to give back the derivative of f with respect to x. So we just use the definition of a derivative as a limit and return f prime. Now we need an h variable, so what we're going to do is this. We can't really make h go to 0, but what we can do is make it a really small value and hope that's good enough. Let's define square so we have something to differentiate, and times 2 will be the derivative of square. So square of 5 is 25. Times 2 of 10. Well, that's almost correct. I mean, it's supposed to be 20. It's pretty close, not exactly right. If we import math, we can get access to e and natural log. So the derivative of natural log is 1 over x. So let's try to do that. And let's just define 1 over x like this. So 1 over 2 is 0.5, 1 over 3 is a third. And if we use our derivative function, we can see It gives a close approximation to what we want, not exactly though. So the nice thing about this is you don't have to, implement the power rule, the product rule, and the quotient rule because, we're just using the definition of the derivative and it works on any one argument function. So now what we can do with this is find root is an implementation of Newton's method. So the root of a function is whatever x value where it crosses the x-axis. So we want to find this x value. To do this, we have an initial guess of 1. We take that guess and subtract f of guess and divide that by f prime of guess. So here's a polynomial, 3x cubed minus 6x squared plus 5x minus 70. So let's reload the file. We can call a polynomial on a single argument like 5 or with 0. And now we want to find the root of this polynomial. So x equals 3.46 something something something. Now I'm going to show you that that's actually accurate. So let's copy this and go to Wolfram Alpha and ask it to solve this equation. So let's do approximate forms, then more digits. So it's 3.463707. So let's look back at what we have. 3.463707. All right. Next up is 245,428. 24543. So 428 rounds up to 43. So yeah, it's pretty accurate. We applied Newton's method basically for 100 iterations, so that's why we could get such an accurate answer. All right, cool. So thank you for watching the second video. Hope you enjoyed it. There will certainly be more to come, and I really appreciate it. Thanks.